In this lesson, we will begin by looking at the materials from which aircraft structures are made, and we will look at the effects of corrosion on these materials. We will also examine the effects of a hard landing on the aircraft structure, and we will look at failure statistics and their effect on flight safety. We will finish the lesson by having a quick look at the maintenance methods employed to keep aircraft in a safe and airworthy condition. Modern aircraft are constructed mainly of aluminium and its alloys, with smaller amounts of steel and titanium for the major structural components. Composite materials are used extensively for more lightly loaded structures. Each material is chosen for its particular properties with regard to the fatigue strength, wear resistance, strength to weight ratio, fire resistance, and so on. Aluminium alloys are the most widely used metals for structural use due to them having a good strength to weight ratio. Duralumin is an aluminium and copper-based alloy which has poor corrosion resistance except when clad with pure aluminium. It has good thermal and electrical conductivity and good fatigue resistance, but it is difficult to weld. Aluminium-clad duralumin is the most popular material in use for airliner skins. Steel and its alloys are relatively heavy, but can be made very strong. They are used only where strength is vital and weight can be ignored, for instance, in undercarriage units. Titanium is much lighter than steel, but it is just as strong and can be used where fire protection is required, for instance in engine firewalls. Titanium has good strength, and it retains this strength and its corrosion resistance up to temperatures of 400 degrees Celsius. It is, however, expensive to produce. The SR-71 Blackbird was the first aircraft to make extensive use of titanium within its structure, paving the way for its use in modern fighter and commercial aircraft. The Boeing 777 uses some 58 tons of titanium in its construction. Magnesium alloys are also used, their principal advantage being weight. Magnesium alloy has an excellent strength-to-weight ratio, aluminium of the same strength being 1.5 times heavier. Magnesium alloy has poor elastic properties, so its use in primary structures is limited. It is often used in the construction of gearboxes. Composite materials are becoming more and more used in aircraft construction. They are made up from layers of fiber, carbon, glass or Kevlar, molded into the required shape with a hot plastic resin, which is normally epoxy. Carbon fiber reinforced plastic is used where structural strength is required. It can be produced with the same strength as an aluminium alloy, but with a weight saving of about 20%. Glass fiber reinforced plastic does not have the same structural strength, but is often used for fairings and non-load-bearing panels because of its light weight. Kevlar has very low electrical conductivity and high fire resistance. Aircraft cabin doors, overhead bins, and bulkheads may be built with honeycomb cores made up of Kevlar. Composite materials have good resistance to corrosion and can be easily formed into complex shapes, but their fatigue behavior is different to that of conventional metal alloys. Metal structures suffering fatigue retain their design strength up to a critical point, after which failure occurs very rapidly, whereas composites lose their properties gradually. Interest in composites for structural use is due to their high specific strength and specific stiffness, allied with their ability to retain these properties at high temperatures. The Airbus A380 uses a significant amount of composite material in its construction. The tailplane, for instance, is almost entirely constructed from carbon fiber reinforced plastic. Corrosion is the slow destruction of metal by electrochemical reaction. It is one of the most persistent defects found in aircraft. Rectification of advanced corrosion has been known to take thousands of man-hours. In fact, more than 10% of engineering downtime is spent in dealing with corrosion problems. It is therefore essential that it is recognized at the earliest possible stage, and that effective preventative measures are taken. When a metal is exposed to the air, oxygen in the air reacts with the bare metal to form an oxide film which adheres to the metal surface. This oxide film forms a barrier between the air and the metal surface, which can protect the underlying metal from further attack. A good example of this is the Statue of Liberty. It is clad in copper. This has developed a green copper oxide coating which protects the metal from the elements. With the exception of oxidation, all other corrosion takes place when the metal is in contact with water, either as a liquid or as water vapor in the atmosphere. Corrosion is mainly electrochemical in character and occurs in conditions that permit the formation of minute electrical cells in or on the attacked metal in the presence of an electrolyte. It will also occur when a difference in potential exists between the different constituents of an alloy, or where dissimilar metals are in contact with each other. The degree of corrosion is proportional to the amount of impurities in the water, the impurities being due to industrial pollution which has high sulfur content, or by airborne salt particles when operating over the sea. The resultant action is that the metal undergoes a chemical change. The attack may extend over the entire surface of the metal, or it may penetrate locally, forming deep pits, or even follow grain boundaries inside the core of the metal. The weakening effect can be aggravated by stresses in the metal due to external loads, or there may be residual stresses from the manufacturing process or method of assembly. The three types of corrosion that we are going to look at are surface corrosion, intergranular corrosion, and stress corrosion. The surface corrosion on ferrous metals, other than stainless steel, can be recognized as a reddish-brown powder, commonly known as rust. The surface of aluminium or magnesium can become covered in white to grey powdery deposits. On magnesium, there may also be deep pitting of the surface. The surface of copper and its alloys may become covered in blue-green salt deposits. Surface corrosion is the least damaging. It is relatively easy to spot, so it can be identified and dealt with at an early stage. The microstructure of metals and alloys is made up of crystals or grains, separated by grain boundaries. Intergranular or intercrystalline corrosion is a localized attack along the grain boundaries, or immediately adjacent to grain boundaries, while the bulk of the grains remain largely unaffected. it penetrates the core of the metal along the grain boundaries. The rate of attack is not limited by the lack of oxygen and is accelerated if applied or residual stresses are present. Repeated, fluctuating stresses cause separation of the grain boundaries, accelerating the spread of corrosion. As a result, higher stress concentrations can occur in the remaining sound material, thus producing cracks which can spread, leading to component failure. This is a very dangerous form of corrosion, as detection is difficult and serious weakening can occur before any external evidence is visible. The only surface indication may be a series of hairline cracks, probably only visible through a magnifying glass. There is no effective method of determining or of limiting the loss of strength which will occur with this type of corrosion, so when it is detected, the affected part must be immediately rejected. A combination of a steady tensile load and corrosive environmental conditions produce a form of metal fatigue known as stress corrosion cracking. The stresses may be built in during manufacture, introduced during assembly, or may be applied during operation. Metal under stress corrodes more rapidly than unstressed metal. It usually begins with pitting at the surface. This increases the stress at the pit, causing a crack which can extend under the combined action of corrosion and load until failure occurs. There is generally very little evidence of corrosion and no apparent loss of metal. This type of corrosion is often not spotted until a serious failure occurs. An aircraft's landing gear is designed to withstand landings of a particular maximum all-up weight and a maximum vertical descent velocity of 10 feet per second or 3.15 meters per second. If either of these parameters is exceeded during a landing, then the aircraft may be damaged. Damage may also be caused to some aircraft by landing with drift applied, or by touching down with the nose or tail wheel first. Some aircraft are fitted with hard landing indicators, which give a visual indication that specific G-forces have been exceeded. But in all cases, if the crew suspect that a hard landing has been made, then all details, including aircraft weight, fuel distribution, landing speed, rate of descent, and any noises indicative of structural failure, must be reported so that an inspection can be carried out prior to the next takeoff. The damage which may be expected following a hard landing will be concentrated around the landing gear, its supporting structure in the wings and fuselage, around the wing and tailplane attachments, and the engine mounts. Secondary damage may be found on the fuselage skin and structure, depending on the configuration and loading of the aircraft. On some aircraft, it is specified that if no damage is found in the primary areas, then the secondary areas do not need to be inspected. However, the precise inspection requirements vary from aircraft to aircraft, so reference must be made to the appropriate maintenance manual. It is important for pilots to have an understanding of the fail-safe concept and the way it is designed into modern aeroplanes. The following is a summary of the required relationship between component failures, their effect, and the possibility of them happening as required by the certification specifications from EASA, as detailed in CS25. Failures are classified into 5 groups, according to the severity of their effects. The lowest class is no safety effect. This is self-explanatory. It will have no effect on the operation of the airplane. Next is minor failure. This failure condition will significantly reduce the aeroplane's safety, but the crew's actions required will be well within their capabilities. There may be some physical discomfort to passengers or cabin crew. Third is a major failure. This will lead to a significant reduction in safety margins or functional capabilities, a significant increase in crew workload, possible flight crew discomfort, and possible physical distress, including injury to passengers or cabin crew. A hazardous failure will reduce the capability of the aeroplane or crew to cope to the extent that there will be a large reduction in safety margins. The conditions may cause physical distress to the flight crew so that they are unable to perform their required tasks accurately or completely. There may be serious or fatal injuries to a small number of passengers or cabin crew. Finally, a catastrophic failure will result in multiple fatalities and probable hull loss. Shown here is a summary of the failure classifications. Spend a moment studying it before moving on. The allowable likelihood of a failure occurring is defined in both qualitative and quantitative terms. A probable failure condition is one which is expected to occur one or more times during an aeroplane's lifetime, or less often than once every 1,000 flight hours. A remote failure condition is unlikely to occur to each aeroplane during its life, but it may occur several times when considering the life of a number of aeroplanes of the same type. Or it may occur less often than once every 100,000 flight hours. Extremely remote failure conditions are not expected to occur to each aeroplane, but they may occur a few times when considering the total life of all aeroplanes of the same type. Or they may occur less often than once every 10 million flight hours. Extremely improbable failure conditions are so unlikely that they are not expected to occur during the entire operational life of all aeroplanes of one type, or less often than once every 1,000 million flight hours. The simple rule is that the more severe the outcome of a failure, the less likely must be the possibility of it happening. As you can see from the chart, a catastrophic failure must be extremely improbable, whilst a minor failure may be probable. Spend a moment studying this chart. It shows in a diagrammatic form the required relationship between the probability and severity of failure conditions. As well as obeying the rules about the probability of failure, modern aeroplanes are designed around the fail-safe concept. The basic objectives used to achieve this are that a single failure of any single element of any system or subsystem should be assumed. This failure must not be catastrophic. A second failure in the same system on the same flight should not be catastrophic unless its joint probability with the first failure is extremely improbable. In order to achieve this, the fail-safe design concept uses one or more design principles or techniques to ensure a safe design. Redundancy and backup systems are used to enable continued function after failure of one or more systems. A good example of this is the use of multiple engines. Systems and components are isolated and segregated so that failure of one does not cause failure of another. For instance, aeroplanes are designed with multiple independent hydraulic systems with no transfer of fluid between them. Systems are tested for proven reliability so that multiple independent failures are unlikely to occur on the same flight. Airlines using large twin-engine aeroplanes for extended range operations have to continually monitor and prove their engine reliability in order to be allowed to operate. Failure warning systems are provided for the crew to be made aware of such failures. Flight crew procedures are developed to limit the effect of any failure. A checking system is used to ascertain a component's condition. Components are designed to sustain damage without failing, or to direct the effects of a failure in a way that limits its safety impact. And lastly, components are designed with margins beyond their planned life. On the screen is a summary of the design principles and techniques used to produce fail-safe aeroplanes. Spend a moment studying it before moving on. For aircraft structures and components, there are two maintenance methods in common use. These are known as hard-time maintenance and on-condition maintenance. Hard-time maintenance is a preventative primary maintenance process. It requires that an appliance or part be periodically overhauled in accordance with the company's maintenance manual, or that it be removed from service. An example of this would be a part that must be removed from the aircraft after X amount of flight hours or calendar years for an overhaul, or disposal if it is a non-repairable item. On-condition maintenance is also a preventative primary maintenance process. It requires that an appliance or part be periodically inspected or checked against some appropriate physical standard to determine whether it can continue in service. The purpose of the standard is to remove the unit from service before failure during normal operation occurs. That ends this lesson. You should now be familiar with the various materials used in aircraft construction and the advantages and disadvantages of each material. You should know the causes and effects of corrosion. You should understand the effects of a hard landing. And you should have a good knowledge of what constitutes a fail-safe aircraft design. Finally, you should understand the difference between hard time and on-condition maintenance.